Ladies and gentlemen, members of Jesus College and guests, welcome to Farrer & Co. My name is Helen Sculthorpe and I was at the college from 78 to 81. On behalf of the firm, it's a real pleasure to welcome you all. We're delighted to host this event on behalf of Jesus College, and it's been a pleasure to work with Hannah and her colleagues in the development office. This is the second Jesus College event the firm has hosted here, and we hope it'll give you all opportunity to renew your old associations and create some new ones. There are 4 members of Jesus College at Farrers, and all are here this evening. There are Rachel Lewis in our employment team, Gary Hopkins, who's our risk and compliance manager, Megan Jobson, and myself in the property team. We're not sure if we have the largest representation of any Oxbridge College here, but we're sure we must be nearly there. It's a particular pleasure to welcome the college principal, Professor Sir Nigel Shadbolt, this evening, and we look forward to hearing more from him about his latest book, The Digital Ape. We're all being exposed increasingly to artificial intelligence in its good and its bad forms, so it's a very topical area. Sir Nigel, you're very welcome. Just remains for me to hand over to the principal and to thank you all very much for attending. Thank you.
Thank you. Well, thank you to Farrers, and thank you to Helen for organising and helping us put on this event this evening. With various designations, the college, the university, and the other organisation I chair and founded with Tim Berners-Lee, the Open Data Institute, I'm going to tell you about the Digital Ape. Why the Digital Ape? Well, we stole the idea from this. Now, I bet quite a few of the people in this audience will remember this book, okay? It was a landmark book. It really was a bestseller. It was followed by another book, The Human Zoo. This was a zoologist looking at the human condition, kind of putting on their white coats and permission to tell scientifically dirty stories about us, because we're primates with basic urges. You'll notice here that Bridget Brophy of the Times said the chapter on sex is his best. Well, I don't know about that. I think it's all pretty good, actually. But it's a really interesting. It also allowed us, let me take the book, to do the unforgivable on the first page of a book. Really, we simply quoted from Desmond Morris, opening paragraph after our opening paragraph. He said, there are 193 living species of monkeys and apes, and 192 of them are covered with hair. The exception is a naked ape, self-named Homo sapiens. This unusual and highly successful species spends a lot of time examining his higher motives and an equal amount of time studiously ignoring his fundamental ones. He's proud that he has the biggest brain of all the primates, but attempts to conceal the fact that he has the biggest penis, preferring to accord this honour falsely to the mighty gorilla. Well, that's a way to start a book, actually. So we borrowed the time. But the whole thesis of our book is that whilst this view of ourselves is hugely important, and we begin in the first chapter to talk about our origins a lot, it's not our purely our biological heritage that we have to really concern ourselves with. It's the ape in a digital context that is fundamentally important. So I will unpack that. However, we start by acknowledging the following really important fact. And it's a fact that has become much more established just in the last few years than it ever was in academic research or indeed evolutionary thinking. This is a distant forebear. This is Australopithecus afarensis, one of our hominid ancestors. 3.5 million years ago, this ape was making tools, knapping flints. Okay? This flint was found in a deposit 3.1 million years old. No one had a clue that shaped tools existed that were that old. What it means is that for 200,000 generations before we even appeared on the scene, our forebears were inventing and developing a technology. And more particularly, that technology was inventing them. Because the technology allowed them to ultimately master their environment and achieve extraordinary things. When Homo sapiens appeared on the scene, this individual or her like were making exquisite tools. We see something very interesting when we actually examine, as we can nowadays, brain stimulation. So Dietrich Stout is a professor in the United States who images the brains of people knapping flints. It takes about 10,000 hours to be good enough to make a flint like that. It's a lot of practice. It's a huge amount of activity. And it requires a lot of coordination to see the tool in the raw material, to imagine how to plan and execute a complex set of coordinated activities. It's thought that the activity of doing that in a group was one of the driving functions in the development of language and coordination. It was certainly a driving function in the earlier hominids for fine motor control, gaining all sorts of precision in the hand-eye coordination process. We didn't invent our technology entirely. Our technology partly invented us. So when people talk about the new world where this technology is running ahead of us, it's always been like this. And indeed, when you look at the imaging from Stout's work, the areas in blue are areas of the brain that are activated when the primitive and the modern tools that I showed you there are made. So Aldervan tools and so-called Archeolian tools, millions of years of tool types, but basic capabilities are recruited. The red areas are recruited when the modern tools are made. So the brain is actually recruiting different areas for the more complex tool making. So we think this tells us something very interesting. We spend some time in the book examining this whole question of how our technology has shaped us. It wasn't just tool making. Taming fire outsourced digestion. We could have more efficient digestive tracts. We didn't have to lumber around on, it was a much higher calorific value food that could be eaten and maintained. And again, that seemed to be a hugely important part in our evolutionary origins. The other thing we point out in the early chapters is one of the challenges we face in the modern world is being inspired, awed, overwhelmed by the products that we have built. And this is difficult because I put my prop away now. I always carry my phone, but I thought it might interfere with the radio mic, so I put it away. We'll just wave it about. This thing here, this remarkable magical object that most of us carry around, or a variant of it in our pockets. So back in the day, you would gaze at this achievement and we'd be awed and impressed by it, or Salisbury Cathedral, or some other construction where you could see the late... Well, that's a bad example, isn't it, nowadays? That's obviously why they turned up to look at it. It is so also inspiring, as we know. The whole notion of being impressed by the works of man, humankind. And there's a wonderful, Blake's wonderful augury. I love this. It's to see a world in a grain of sand and a heaven in a wildflower, infinity, hold infinity in the palm of your hand and eternity in an hour. Now, we recruit that in an early chapter to make the following point. Our world is literally built out of sand. The devices that have powered us into the 21st century are microchips. And this is a layout, it's not even quite up to date yet. We stopped in 2014 with the Apple A8 chip. But on the left is an axis, which is the number of transistors you could get on a particular area. And along the bottom is a year count, 70, 72, 74, and so on. This is a logarithmic linear graph. It's a straight line. It tells you that computing power is doubling every 15 months thereabouts. This is the well-known Moore's law. You just have to sit for a moment and think about what that means. It means that when I began my PhD to now, the devices I can run my programs on have engrossed and multiplied by a millionfold, 10 to the 6 improvement. Had we improved air flight that fast, I'd be flying from here to Sydney in a quarter of a second. Well, I wouldn't, because I'd be smeared all over the fuselage, but the concept of improvement is extraordinary. And again, it can be really hard to stand back and appreciate the complexity. So we take the A8 chip and we go on a bit of a journey now, and we're going to kind of zoom into this is a silicon wafer that would have produced a whole range of those chips being etched with light beams to specify component architectures that are on the scale of nanometers. This is already somewhat old hat. This old hat is 15 nanometers, which means I could get 450 of those components inside a single red blood cell. Okay. It's hard for us to imagine the scale, the level of human ingenuity that is packed into that device. But I think it's important we do. It's important we realize, and because they're so ubiquitous, they become in some sense an object of little remark. Well, they are remarkable. They're remarkable also because, unlike the stone tool I showed you, no human on Earth could make this. No single human. No single human possesses all the knowledge to make this, unlike the hand axe. So we've traded the thing again, in the second chapter we talk a lot about this hyper-complex environment that we've built where no one understands all of it and we're all deeply interconnected. And there are very, very significant dependencies between the manufacturing of these devices and the software that runs on it and all sorts of consequential issues around that, from security to explicability to this fact. The fact that on this device there are at least 20 or 30 manifestations of the results of artificial intelligence research. When I began, the thought of a device which could recognize your voice, interpret it, parse it, structure it, work out you're asking it a question, go to a world database and answer a question like, when was Michelangelo born, would have been, well, in 1978, when I started out, I'd have thought we had solved the general AI problem if we could do that. Let alone recognize my face in a crowd of faces, let alone book an appointment for me, let alone work out the fastest way to get from A to B, taking into account the contingent traffic conditions. This is all commonplace, almost unremarked, until we, again, examine this challenge. Try making one of these. This was a great experiment. Thomas Thwaites at the Royal College of Art tried to make a toaster. A £5 toaster. What would it take to make it from first principles? To mine the ore, to make the plastic, to shape the plugs, to shape the filaments. It's a sorry thing. It took nearly 2 years to do. It demonstrated just how far out of the reach of each and every one of us maintaining the products of our current society are. So the first part of the book is a lot about this kind of scene setting, partly to get people to stand back in a way a little bit like Desmond Morris did, to stand back and look at man as a primate, to stand back and look at us as both the architect of a remarkable technology and in some sense having done a deal that we become deeply interdependent with both the devices and their manufacturing process. And more than that, a 4-year-old child growing up today faces a future in which intelligent machines will be a part of it, and we'll talk about what that means in a moment. But also we're entering a phase where we might be able to upgrade ourselves. So with technologies like CRISPR, this technology that allows you to essentially edit the human gene, we can change, perhaps even upgrade our own and other species' fundamental operating and hardware systems. That's just the most remarkable thing. And people say, oh, the AI, it's an existential threat to humanity. We'll come on to that argument in a moment. This, I think, is a much bigger deal and likely to be fraught with really substantive ethical and moral choices, and it's happening right now. So, a few years ago, Stephen Hawking famously, of course, called our attention, brilliant man that he was, to the threat that artificial intelligence posed. He had had his speech software recently upgraded actually a product of an AI company called SwiftKey in Cambridge, who upgraded his speech synthesis system. So his very distinctive voice that you heard, it was a very laborious process to get those utterances out. And with a particular software upgrade, which used predictive text methods to anticipate what he wanted to say, the kind of thing you get with your text completion now on your phone, he suddenly started to think about what this meant in terms of the future, where software was going. And he pretty quickly got to this, which is Hollywood's notion of the future of AI is always some mad, bad, and dangerous to know robot, like Terminator. I wonder why. Well, this is Boston Dynamics' latest mobile robot. Boston Dynamics come in for a bit of flack, actually, because it's often claimed that their kind of sequences like this are a bit of a stunt. But actually, this is hard to do. Running over uneven terrain is non-trivial. Just a few years ago, this was beyond any humanoid robot, okay? And we're there. So you start to see why people might be getting a little bit spooked by all of this. Since about 2015, I've been writing articles, this one appeared in Wired, on what our approach to AI should sensibly be at this point. And I've always said, it isn't the artificial intelligence you need to worry about, it's the natural stupidity. And I come on to that in the sense that one of the things that really worries me is our failure to understand the consequences of some of these technological innovations. So let me spend a little bit of time talking about the technology itself and just unpacking what is all this AI about, really. My first success in AI terms was in the mid-'80s when we took a task which human beings were pretty good at and built a program to do it. This was the era of so-called knowledge-based or expert systems. For those of you in the know, and there may well be people, that's a great thing with Jesus alumni, there may be a chemical engineer or two in the room. This is a process flow diagram. It specifies how to make a particular chemical through a series of process elements. It's a logical circuit diagram for making a particular compound. And our system took that diagram and produced this. You can see it must be about 1980s, poor graphics, but all the rest of it. But the cleverness was we worked out how to lay out in 3 dimensions that flow, that process flow. What we did, of course, we spoke to lots of chemical engineers and we tried to make explicit their expertise in programs, so-called rule-based programs that would say, if you have this and this and this, then do this. If you have these 2 elements, keep them far apart because you'll violate a constraint that means they might explode or you can't service them. So we had lots and lots of rules and constraints. This was quite a successful product. It was acquired by an American process control company called Aspen Tech, and I got my first taste for spin-outs, that you could take an idea from a lab and make it work in the world. But it also taught me some very hard lessons about the difficulty of building general artificial intelligence. Because in this diagram here, human engineers have tons of common sense engineering knowledge, tons of knowledge that you and I have as well, that we don't think of. It's not represented in here. In a particular part of that diagram, there is no reference to pumps to get stuff from one place to another. Why? Because an engineer knows that if you want to get stuff from up there to down here, you can use gravity. Okay? Gravity flow. Gravity flow wasn't in the earlier diagram. It's not in the specification at all. It's your common sense knowledge. Common sense knowledge is one of the great brick walls that still confronts all machine intelligence. That doesn't stop us doing remarkable things, and it happens periodically. Now, this is one of my favorite pictures of Garry Kasparov in 1997, losing a game and actually ultimately the match to IBM's Deep Blue. He was very spooked by this at the time. He said at the time he thought it was actually a little big conspiracy at one stage, and then he said, more brilliant book that he's written recently, on reflection, he said, I'd played a lot of chess computers, but this system, I could smell a new kind of intelligence across the table. Kasparov at that time did something very interesting. Chess is complex. Chess has a branching factor of, well, in the middle of a chess game, if I've got 4 moves and you've got 4 moves, on average you've got about 650 billion options to look at. It's complex. No machine could possibly play chess by searching a proportion of those moves. By 1997, that's precisely what you could do. Deep Blue was evaluating between 200 and 400 million moves a second. Okay? No human plays chess like that. In fact, all the effort in chess playing prior to that had been in what was called cognitive emulation. Let's try and work out how humans do it and build a program that works like that. Well, with the increase in speed and power, you can achieve superhuman performance with non-human methods. And what we'll see time and time again is that's what's happening. That machine at the time was a state-of-the-art supercomputer, and now we have off-the-shelf products and software packages which can do just as well as Deep Blue did. And of course now, the interesting thing is that chess hasn't died. People play new kinds of tournaments now. They play combinations of machines and people. They still play between each other. It's just, there's one thing that machines can do very well. Who knows of Watson in the room? A few of you will. Yeah, a few. Okay. Watson was the product, IBM again, actually. So this time you think, oh, this is good. This is all IBM. But what IBM did in the next 15 years was look at the whole business of trying to do something more impressive, not just beat the world's chess player, but beat something that would look like human talent that would be surprising and interesting. They chose the US game of Jeopardy. Jeopardy, you'll see immediately how it works.
It's going to change how we interface with information.
People are going to ask, how did it do that? How did it accomplish this task, which before we thought only humans could ever hope to do?
David Hume held this view that sense and experience are the sole foundation of knowledge. Watson.
What is empiricism?
Watson is a question answering system. A question can be posed in natural language, and having read a whole bunch of information, data, documents, come up with a very precise answer to that question.
It's an information-seeking tool that's capable of understanding your question to make sure that you get what you want, and then delivers that content through a naturally flowing dialogue. Do you have one of those? I don't have one of those, right?
It's a human standing there with their carbon and water versus the computer with all of its silicon and its main memory and its disk.
After Germany invaded the Netherlands, this queen, her family, and cabinet fled to London. Maria.
Who is Beatrix?
No. Watson?
Who is Wilhelmina?
That is correct.
Humans communicate very fluently in natural language. And that's where computers struggle dramatically. And that's where we want to make them better.
This U.S. president negotiated the Treaty of Portsmouth, ending the Russo-Japanese War. Watson.
Who is Theodore Roosevelt?
Good for $800.
Jeopardy questions are tricky. They have puns in them, they have little jokes in them.
A famous red-coiffed clown, or just any incompetent fool. Watson.
Who is Bozo?
Nice. Good job, Watson.
Who's Bozo? I think that's rather good. That is impressive. Watson. So when you start to look at Watson, you start with IBM's Deep Blue, you think, well, the machines are on the march. In fact, when Kasparov was beaten, there were headlines everywhere. The machines were going to take your jobs. They were going to wake up and put away with us. This same kind of set of alarmist commentary is around at the moment. Watson is impressive because it is able to analyze language, but it's using traditional computational linguistics methods. It has access to the world's internet knowledge base. Wikipedia. It has access to every question that's ever been asked in Jeopardy. It has access to ... It has lots of knowledge at its disposal. In fact, it's very good at playing Jeopardy. You can't take Watson and have a conversation with you about some other topic, or play QI, or play any other particular game you might think of, or indeed turn it into a general interface for health-based AI, which is what IBM are trying to do without a huge amount of effort. So the system doesn't know how to generalize and learn across domains, but within specific tasks, it's impressive. Now, recently, there's been a new, not a new actually, it's been a technique that's been around for a while, a new wave of excitement in AI based on the concept of neural networks. This is something that a colleague and I were working on back in the 90s. A lot of work on neural networks since about the 1990s. And this is a complex differential equation that's actually talking about how synapses can form links to one another and change their strength depending on the release of particular chemicals, so-called neurotrophins. These are the factors that are used in development to wire up the brain. So this is a fairly faithful model of how nervous systems developed. We actually used it to implement little nervous systems on these little robots here. These robots can trundle around with two motors and they have a skirt of infrared sensors around the edge. These two robots are different. You can see the little spray fan diagrams there. Those indicate how good the infrared sensors are. Turns out that robots, in actual fact, aren't just as accurate as every other kind of robot, every other kind of sensor. They have flaws and defects. Not every sensor works as well. So what you want is to develop a simple nervous system, a neural network, that accommodates to the difference in those two robots' morphology. So, right motor neuron, left motor neuron, those will turn the motors by sending a signal. Set of interneurons, which actually can change and connect through to the infrared neurons. Those represent the sensors going in. A neural network is nothing more than a layer of neurons with connections between them. And what you do is, according to that equation we saw, or some other equation, change the strength. In fact, what we did, we're able to train different optimized networks for the different abilities of those two robots. That's what you can do with neural networks. And what has happened in subsequent decades is that those networks have got deeper and deeper and deeper. And at a certain moment, they broke through to public consciousness. They broke through to public consciousness when a British-based AI company that was acquired by Google, DeepMind, beat another world champion in another very difficult game, the game of Go. But actually, the story started earlier than that. Right, now look here. It started out that it can't play this classic arcade game. If you recognise this, it's Breakout, where you have to control a couple of puddles and get the ball back. There's no idea at all. But after about 120 minutes of training, see how good it is now. Okay, it's got control of the paddles, and it's actually increasing the score. This is 4 hours of training. Any advanced Breakout player will recognise this tactic. It got the ball behind the defence, okay? Now, what's happening there is that the system knows nothing at all about the game. All that's happening is that the pixels that represent that input are being fed into a neural network, a complex neural network. Every pixel is represented as a node. And through time, those layer on layers of networks are learning to associate patterns that correspond to doing one thing, increasing the score at the top there. So these so-called deep neural networks are able to learn the signals that are present in extended amounts of input. That's the trick of deep learning. And of course, it was applied look at the look on Lee Sedol's face, exactly like Kasparov's. Couldn't believe he'd been beaten by this system. What these deep neural networks are able to do is achieve exquisite levels of performance in specific tasks. They are not generally intelligent. They are not going to wake up and put away with us. They are not going to see the end of work. Why not? Well, because the robots that might be on the manufacturing lines are going to produce products, and somebody will have to buy those products. Capitalism, the calculus of capitalism, requires consumers. We will find new ways of transferring wealth to ourselves, and we will find new things for us to do. We have always done that. Whether certain classes of job become automated, we will decide that this job is worthy of remuneration. We will need a whole slew of types of new accountant and lawyer for the new world we're going into, no question about it. It's not going to simply disappear at the hands of a Watson-like paralegal. So what should we worry about? Worry about this, okay? Now, you may have Amazon or Google Home in your house, be completely unfazed by it. At the moment, we have no particular understanding of what and where and how the information is being processed off these things. The rapidity of the deployment of these Internet of Things, these smart devices, is a serious challenge, I think, to us. Again, the chatty digital assistant on the end of this soothing voice may get you to confide all sorts of things in them, may well be, in a sense, a digital companion that keeps you amused and entertained or consoled. But there's nobody at home in the circuits. Just as when you open up Deep Blue or AlphaGo, there's nothing in there that has the slightest sense of a job well done when it won the game. We built them, we designed them, they are task-achieving systems. Even when the soothing voice asks you if you've had a hard day, and what would you like from the fridge, and is your beer cold enough, and all of this kind of apparent intentionality is us projecting onto them. But the real concern is where is your data going and what's being done with it. And another concern is that very shortly, the amount of AI we have on our phones, we have on our devices, we have within the great corporate systems we have available will be packaged and presented to us in very different ways. So the toy of the future, the toy of just about now, will be loaded full of emotion detection responses. It'll be loaded full of software to engage with and chat with its friend and companion. And these devices will become friends and companions of the child on the right there. What kind of world does that look like? And how do we regulate and manage it? And how will we think about the benefits and disbenefits of that? And the truth is that when all of this stuff is being collected and aggregated, its destination will almost certainly be one of these 10 companies. And the interesting thing about these companies is that for the 5 on the top, there are analogues in China and the Far East. So the search engine that is Google has Baidu, or the shopping platform and the cloud provider that is Amazon has Alibaba. And the question we will face there is, do we have the right kind of governance processes? Do we have the kind of right way of maintaining transparency to ensure that the decisions that these companies make, and I'm sure they will say they're doing it to provide great services for us, but they're being held accountable. We end the book talking a lot about the prospects for the integration of humans and machines at scale. I've presented some issues that I think we need to be concerned about and think about, but at the same time, I'm very hopeful of where we will get with this technology in the future. I'm very optimistic. I'm an optimist because, in part, we've already seen, and we see constantly, the products of this unification of humans at scale and our data and algorithms at scale. I'm going to close with a remarkable example of this. It's about 8 years old now, but it's still a testament to the best integration of humans, algorithms, and data at scale. This is a picture, very poor picture, as you can see. There's no detail on it, of Haiti's capital city, Port-au-Prince. They were too poor to have a detailed map of their capital city. Nobody had actually commissioned one. You may remember that in 2010, there was a huge earthquake. It's visualized here by an organization that collects geospatial data. What you're seeing here through January the 10th and over the next 12 days are data uploads. Emergency relief responders going in with GPS and uploading their data as they walk the streets of a ruined capital city, and the algorithms stitch this data together. Stitch it together to produce an extraordinarily detailed map of a ruined capital over which they were able to deploy humanitarian relief. That view of ourselves as being augmented by our technology, augmented intelligence, is the thing that I look forward to. It's where we need to get the balance right, using our technology to assist us in the most challenging problems we face. So I'm going to end it there. So thank you very much indeed. Thank you.